Welcome, high school teachers. Today we're going to carry on in this course on Archimedes and the law of the lever. And we're going to be looking at vectors and barycentric coordinates. So we're looking to extend Archimedes' understanding of balancing and one-dimensional levers to the two-dimensional situation. That's going to bring in the important topic of vectors and allow us to introduce a very interesting idea of barycentric coordinates. So last time we were talking about one-dimensional levers and mass distributions on a one-dimensional space and the center of mass of a mass distribution. Here is a lever or a rod that has an unequal mass distribution. It's not a uniform rod because there's a mass, heavier mass, glued to the end here. So the center of mass is actually somewhere around here. It will balance somewhere around here. Now, it's an interesting thing that you can show your students, that you can find that center of mass by a relatively simple-minded mechanical procedure. If you just support the rod with your two fingers at the ends, and then bring your two fingers together, you don't have to make any particular effort. You just bring your fingers together, and automatically the physics of the situation is such that you end up with your fingers together pretty well at the center of mass. Now that same kind of phenomena happens also in two dimensions. So here is a cutout of Australia. And if we think of that as a mass distribution, it will also have a point of balance somewhere. How could we find that point of balance? One way is to form a tripod with three fingers to balance the mass, and then bring those fingers together. You don't have to make any particular effort. You just bring them together, and once they are pretty well together, then you're balancing at the center of mass. So today we're going to analyze this kind of situation by working in the Cartesian plane, and in particular we want to remind you a little bit about important facts about vectors. So here's the Cartesian plane with an x-axis and a y-axis, and this familiar idea that points are represented by ordered pairs. And I'm going to put the points in square brackets. So here's the point A, here's the point B. Now in addition to points, we also have vectors. A vector is a somewhat more subtle thing. It's created by 2 points. So a vector is a directed line segment that goes from one point to another point. For example, this vector v, which goes from A to B. And we write it as the round bracket 1, 2, because you have to go over 1 in the x direction and up 2 in the y direction to go from A to B. Another way of obtaining that vector is to take the difference between the coordinates of B and the coordinates of A. This vector v is the same if we translate it. It's a very nice thing about vectors. So if I take that vector and I move it to some other position, as long as I don't change the length or the direction, then it's actually the same vector. That will still be the vector 1, 2. I could even move it down to the origin. It would still be the vector 1, 2. So here are a few other vectors in this situation. Here is the vector u, which is the vector 3, 1, which actually goes from the origin to the point A, sometimes called the coordinate vector of A. So there's the point A, and here is the vector, which is the coordinate vector of A. Here is the coordinate vector of B. And now we can see a very pleasant aspect of vectors, that we can do a little bit of arithmetic with vectors. We can add them. This vector u plus this vector v makes this vector w. And you can see that geometrically. You go in this direction, and then you go in this direction. The total movement is this one. Or you can see it arithmetically. If you take this ordered pair and you add that ordered pair, then you get that ordered pair. All right, so in addition to points and vectors, we also have lines, of course. And let's talk a little bit about, say, this particular line right here. This has Cartesian equation, 3x plus 2y equals 6. or y equals minus 3 over 2x plus 3. Sometimes in high school, this is a more familiar form of an equation for a line because it's giving y as a function of x. To go from here to here is just a question of multiplying by the denominator and bringing the x and y terms to the same side. They're equivalent ways of thinking about the equation of the line. Note that the x-intercept is this point 2. So when y is 0, x is equal to 2. The y-intercept is when x equals 0, then y equals 3. And the slope is minus 3 over 2. Now there's another important way of thinking about the equation of this line, and that's this one here. It's called a parametric equation for the line, and it's really an equation in the language of vectors. Okay? So this equation is saying that a vector xy on the line can be obtained by starting with the vector 2, 0. We can think of that as being this vector right here. Here's the vector 2, 0. And then adding a multiple lambda of the vector minus 2, 3. The vector minus 2, 3 in this situation is this one right here. The vector from here to here, that vector there, is the vector minus 2, 3. What we're saying then is that if we start with this vector here, and then we add some multiple of this vector minus 2, 3, then we're going to get a general vector on that line. For example, if lambda equals 0, then we're talking about 2, 0. If lambda is equal to 1, then we're talking about this point 0, 3. But lambda could also be a half, or lambda could be 2, or lambda could be a minus 1. We get different points on the line by changing that parameter. Now we want to extend Archimedes' ideas to the two-dimensional situation. And it turns out that his basic law of the lever works almost exactly the same in 2 dimensions as it does in 1 dimension. But the situation is physically more interesting and complicated. Here, for example, is a little planar piece with 4 masses on it at various positions. And a natural question would be, where is the point of balance of this configuration of masses? Or where is the center of mass of this configuration? Now we can actually find it in the same way as we did for the map of Australia. If I just put my 3 fingers here and bring them together, not making any particular effort, I will end up at the center of mass. Now if I put it up here like this, then we can see that these masses are actually in various positions in the plane. All right. And this is a purely mathematical problem. We have various positions. For example, if this is the x and the y-axis, this would be the point 2, 0. This would be the point 1, 2, the point 4, 1, and so on. We would have mass of 1 at this point, mass of 1 here and here, mass of 2 there. And we want to know where is that center of mass. So that's the situation where Archimedes' law of the lever is basically the same formula as we saw in the one-dimensional situation. Here it is. It's that if we have, and this is the planar version now where I put things on the board so we can see various masses, say M1, M2, M3, M4 at positions points A1, A2, A3, A4. And here is the center of mass that we're trying to find, C. And Archimedes' law says that C is the center of mass of, in general, masses M1, M2 up to Mk at points A1, A2 up to Ak, precisely when this moment condition is satisfied. It's a condition about moments adding up to 0. So M1 times C1A1, that's the vector from C to A1. We might call that V1. Plus M2 times V2, plus M3 times V3, plus M4 times V4, and so on. That total vector has to be 0. That's the condition that C, the center of mass, has to fulfill. Now let's have a look at this example here in this particular case, where we're going to actually work it out in a slightly different way by using the vector form to introduce coordinate vectors for these various positions. So when we're working with vectors, we like to replace points with vectors. So instead of thinking about that point A1, let's consider the vector from the origin to that point A1. Let's call it the vector A1. That's the coordinate vector for that point A1. Similarly, let's introduce the coordinate vector for the point C. That will be the vector C. And we could do the same for the other positions as well. When we do that, this equation can be rewritten in the following way. So let's look at this vector v1 going from C to A1. In this triangle here, we have a vector C here, a vector v1 here, and a vector A here. We can see that C plus v1 is A1. And so this vector v1 is the difference between A1 and C. So I'm going to replace this vector CA1, or v1, with the difference between the vector A1 and the vector C. So we're rewriting this in terms of the coordinate vectors of the various points involved. And now I can do the same thing for the next one, m2 times the coordinate vector a2 minus c. And I can keep going up to k terms, if there are such, mk times ak minus c equals 0. And now we can rewrite that equation as m1a1 plus m2a2 all the way up to mkak. And we'll bring all the things involving c to the other side, equals m1 plus m2 all the way up to mk times c. And if we write that whole sum of the masses as capital M, like we did previously, then we see, therefore, that C has to be 1 over M times M1 A1 plus M2 A2 plus all the way up to M K A K. And that's a vector form for the center of mass in terms of the masses m1 through mk and the position vectors of the points a1, a2 up to ak, where those masses are. This is a direct two-dimensional analog of the one-dimensional Archimedes Law of the lever. And it's really this beautiful formula that allows us to make all kinds of calculations and introduce barycentric coordinates. Okay, now let's have a look at an important special case. When we just have two masses, m1 and m2, at 2 points, a1 and a2, in the plane. We have these two masses, and we're interested in where the center of mass is. So Archimedes' law basically gives us this formula for the center of mass, but it's in terms of vectors. It's in terms of the vector a1 from the origin to a1, vector a2 from the origin to the point a2, and the vector c, which is the coordinate vector of the center of mass. Okay, now I'm going to do a little bit of manipulation to this equation to get it into another form that will connect directly with our parametric equation of a line that we talked about in the first slide. Let me rewrite this. Let me rewrite it as the vector a1 plus m2 over m1 plus m2 times the difference a2 minus a1. Let's see why that's true. The coefficient of a2 is m2 over m1 plus m2. That's the same as it is there. And the total coefficient of a1 is 1 minus m2 over m1 plus m2, which is the same as m1 over m1 plus m2. So those really are the same things. So what we're really getting is something of the form a1 plus some multiple, lambda, of a2 minus a1. All right, on the diagram, what this is saying is that this point C can be thought of as being obtained by taking the vector a1 and then some suitable multiple of this difference vector, a2 minus a1. That's the vector in green here that goes from the point a1 to the point a2. It's the difference between this coordinate vector and this coordinate vector. So the center of mass is actually on this line, which is only reasonable. But in fact, we know exactly what this parameter is. The parameter is related to the masses by this equation here. And so, for example, if we imagine that one of those masses is, say, fixed, say, suppose that m1 was fixed, and we think about moving m2 or changing m2, well, then this parameter is going to change, and this center of mass is going to be moving around. So basically, by adjusting the masses, we can get that center of mass to be wherever we want in this interval. In fact, if we're going to be a little bit more general and also include negative masses, then we could even make this parameter negative or bigger than 1. So we could also get at points that are outside the interval this way. So let me show you just specifically what the different values of lambda correspond. If we go to here, then this point here would be the situation where lambda is equal to 0. And when lambda is equal to 1, that would be this point right here. And halfway, when lambda is a half, we would be at the midpoint. If lambda was equal to, say, 3/4, well, then we would be somewhere over here. If lambda was 1/10, we would be somewhere over here. So as lambda goes from 0 to 1, we are moving from this point to this point. We're covering that interval from a1 to a2. Another way of writing this in terms of lambda, go here, is to think of it as a1 times 1 minus lambda. This is another very important way of thinking about this. This is a combination of the vectors a1 and a2, where these two coefficients add up to 1. All right. This is an important kind of configuration called a convex linear combination. Convex linear combination. That's referring to the fact that the sum of the two coefficients equals 1. It's always 1. And when the sum of the coefficients is 1, it means that we're necessarily describing the line that passes through those two vectors. All right, great. Now let's extend these ideas to 3 masses on 3 points. And we get a whole new world of possibilities opening up for us. All right, so here are 3 points, A1, A2, A3. And we're supposing that there are masses M1, M2, M3 on those 3 points. And even though we're on a plane like this, we're actually thinking about it as being a horizontal plane. There's 3 weights on a board. And we're interested in where do those weights balance. All right, so Archimedes tells us that the center of mass, point C, is going to have coordinate vector given by this expression in terms of the coordinate vectors of A1, A2, A3, which I'm not drawing, but they're there. Okay, so A1 is this vector, little a2 is that vector, little a3 is that vector, and the little c vector, maybe I'll draw that one, it's that vector there. Right. And the expression is that it's m1 over capital M. Capital M is just the sum of the masses. So m1 over capital M times a1 plus m2 over capital M times a2 plus m3 over capital M times a3. So it's of the form lambda 1 a1 plus lambda 2 a2 plus lambda 3 a3, where these 3 numbers have an interesting aspect. First of all, they're all positive. Well, assuming that the masses are positive, then the numbers are positive. But moreover, they add up to 1, because m1 plus m2 plus m3 totals the denominator capital M. So the sum of these 3 coefficients is 1. So again, that's a convex combination. We call that a convex linear combination of A1, A2, A3. So we're seeing that this point C has a coordinate vector, which is a convex combination of the coordinate vectors of A1, A2, A3, where these coefficients are determined by the masses. And now conversely, we can think about this as kind of a coordinate system on the interior of the triangle. Because basically any point in the interior of the triangle could serve as a center of mass if we choose appropriate weights on the 3 points. If we want our center of mass to be very close to A3, we just have to make this weight very heavy. Then the center of mass will move there. So this is a way of coordinatizing the interior of a general triangle, which is very useful for a lot of different things. And it's called barycentric coordinates. All right. So this is barycentric coordinates. Maybe I'll squeeze it here. Barycentric coordinates. And they were introduced by Mobius, a very prominent German geometer in the beginning of the 19th century. Okay, so let's bring this to life by looking at a concrete example. So I'm going to suppose that on our triangle here, we actually have concrete masses of 2. So M1 is 2, M2 is 1, and M3 is 3. So the total mass is 2 plus 1 plus 3, that's 6. Here are the 3 masses. The center of mass formula is that C will be 2 over 6A1 plus 1 over 6A2 plus 3 over 6A3, which simplifies to 1/3 A1 plus 1/6 A2 plus 1/2 A3. And here is that point. Okay? And have a look at the properties of this point. It's quite interesting because this is a point of balance of these 3 weights, these 3 masses at the vertices of this triangle. And because this is a point of balance, it means that each of these lines through this point and the vertices of the triangle are lines of balance. It's just like here, if this is Australia, then wherever the center of mass is, if I take a line through that center of mass, I can find a line of balance. Okay, so any line through the center of mass will balance the mass because the mass is supported actually just at a single point at that center of mass. So each of these lines is a balance point of the triangle. And that means that the one-dimensional Archimedes law also is in the situation. Because if we think, say, of this line here, if that's a point of balance of the triangle, then, well, it's going through that point. So the mass M1 is already supported by that line. But in order for these 2 masses to be supported on that line, it means that this must be the center of mass of these 2 points. These masses are in the ratio 1:3. So by the one-dimensional Archimedes law, we know these sides here must be in the ratio of 1:3. Similarly, this being a line of balance, this mass is already on that line of balance. Therefore, this point here must be a point of balance of these 2 masses. There are 2 and 1, so these must be in the ratio of 1:2. Similarly, this is a line of balance. Here we have a mass of 3 and a mass of 2. So this side to this side must be in the ratio of 2:3. All of those ratios are determined by this one vector equation. That one vector equation is responsible for all those ratios. In fact, it's responsible for a theorem, which is almost an immediate consequence here. It's called Ceva's theorem. And it's, in this context here, it's, if you look at the ratio of successive quotients here, 1:3, that ratio, and if we multiply it by this ratio, 2:1, and we multiply it by this ratio, 3:2, so using the same sense as we go around, then we always get 1. And it's kind of obvious because this is going to be in the ratio of m1, I guess m2 to m3. This is going to be in the ratio of m1 to m2, and this is going to be in the ratio of m3 to m1. If you multiply those three ratios, you're going to get 1 no matter what m1 and m2 and m3 are. So that's all very nice, very beautiful application of barycentric coordinates to coordinatize the interior of a triangle, but also to allow us to relatively quickly be able to determine ratios of segments that appear in elementary geometry like this. Let me give you just one more example that you can think about. Suppose I'm interested in the ratio along this Cevian line. I want to know what's the ratio of this segment to this segment. Can you see what that might be? Well, this is still a point of balance. There's a mass of 1 here, and at this point here, this point is supporting the weight of these two. Here's a mass of 3, and here's a mass of 2. So there's kind of a cumulative mass of 5 at this point. This being a point of balance means that this mass of 1 and this mass of effectively 5 here is being balanced at this point, which means that this is going to be in the ratio of 1 to 5 by Archimedes. All right, so in our final module next time, we're going to have a look at some fun activities and applications of this kind of thinking. So you'll have a chance to roll up your sleeves and try your hand at applying Archimedes to interesting situations.